Namaskar to all. Now we are going to see an interesting property of the solutions of the second order linear homogeneous differential equations. In order to see that property, let us see some basic terminologies at first. First of all, let us see the definition for an ordinary differential equation. An ordinary differential equation is an equation that contains both the derivatives as well as the unknown function as mentioned here. Of course, the differential equation depends only on one independent variable as mentioned in these two examples. The first one is an example for an ordinary differential equation with variable coefficient, and second one is an example for an ordinary differential equation with constant coefficients. Because in the first example, as the coefficients of d square y by dx square and dy by dx, the terms x square and x are given. So, the first one is an example for an ordinary differential equation with variable coefficient. But in the second example, we are given only one as their coefficient. So, the second one is said to be an ordinary differential equation with the constant coefficients. In the first example, we can consider y as the dependent variable and x as the independent variable, and in the second example x and y are the dependent variables, t is said to be the independent variable. So from the above explanation, it is clear that a differential equation defines a relationship between an unknown function and one or more of its derivatives. In our day-to-day life, we could see many applications of differential equations. A few of them are listed here, namely electrical circuits, heat transfer, motion, contaminant transport. Now let us see the definition for an ordinary differential equation of order 1. A first order ordinary differential equation includes only a first derivative as its highest derivative, and for first order ordinary differential equation we can have these two as our examples: dy by dx plus alpha y equal to f of x. As we are having f as a function of only one variable, this is said to be an example for linear first order ordinary differential equation. At the same time, suppose we consider dy by dx is equal to f of x comma y. It is said to be an example for non-linear first order ordinary differential equations. Next, let us see the definition for second order ordinary differential equations. When we see the first equation, there we are having d square y by dx square plus p into dy by dx plus qy equal to f of x, where we are having only one independent variable. That's why it is said to be a linear second order ordinary differential equation, where in the second example d square y by dx square plus p of x comma y into dy by dx plus q of x comma y into y equal to f of x is there, which is an example for non-linear second order ordinary differential equation. In our day-to-day life, we could see the CT scan in which the curve comes in the form of zigzag order. That zigzag curve is said to be an example for non-linear second order ordinary differential equation. Now let us see how to find the order and degree of an ordinary differential equation. The order of a differential equation is exactly equal to the order of the highest differential coefficient that it contains. So when you see this example, d cube y by dx cube minus dy by dx whole thing square plus 4y equal to 4 into e power x cos x. This is an example for a linear ordinary differential equation in which we are having the highest order, the derivative with the highest derivative term is given by d cube y by dx cube. So because of that reason, we can say this equation, this differential equation is of order 3 because it includes up to the third order derivative. At the same time, Degree of an ordinary differential equation is defined as the highest power of the highest order differential coefficient that the equation contains after it has been rationalized. So, when you see this differential equation, the highest power of the highest derivative, that is d cube y by dx cube, is given by 1. At the same time, the power of the lowest order derivative dy by dx is given by 2. Even though 2 has given the power of the lowest order derivative, we need to consider only the power number of the highest order derivative, that is the power number of d cube y by dx cube, that is given by 1. As there is nothing there in the power of d cube y by dx cube, even though it is given as nothing, just we can consider 1 in its power, and that 1 is said to be the degree of this differential equation. Now let us see the definition for linear dependence and independence, because we are going to focus a property of an ordinary differential equation by using these linear independent condition. We can say the two functions, any two functions phi1 and phi2, defined on an unit interval I. Unit interval means that's a closed interval, ranges from 0 to 1. Those two functions on this unit interval I are said to be linearly dependent if there exist two constants c1 and c2, not both of them are 0, such that c1 phi1 of x plus c2 phi2 of x equal to 0 for all x in I. So when we have this type of relation c1 phi1 of x plus c2 phi2 of x equal to 0, and from this relation if we are able to get both the constants c1 and c2, not both of them are 0, then we can say the two solutions, the two functions phi1 and phi2 as linearly independent functions. At the same time, suppose from the relation c1 phi1 of x plus c2 phi2 of x equal to 0 for all x belongs to I, if we are able to get both the constants c1 equal to 0 and c2 equal to 0, then we can conclude the functions phi1 and phi2 are linearly independent. Next, we are going to see the definition for Wronskian of any two functions. When we consider L of y as our second order differential equation, that is given in the format of y double dash plus a1y dash plus a2y equal to 0. When we consider this type of second order differential equation, definitely there will be two solutions, and those two solutions may be marked as phi1 and phi2. In that case, let us see how to define the Wronskian of those two solutions phi1 and phi2. The Wronskian of those two solutions phi1 and phi2 is marked by W of phi1 comma phi2 as mentioned here, and it is defined by the determinant, in which along the first row we can have the functions phi1 and phi2. Along the second row we can have the functions phi1 dash and phi2 dash. On expanding this determinant, we are getting that phi1 phi2 dash minus phi1 dash phi2. So this type of determinant is said to be the Wronskian of the two functions phi1 and phi2. By using these properties, now let us see this theorem. Two solutions phi1 and phi2 of L of y equal to 0 are linearly independent on an interval I, if and only if the Wronskian phi1 comma phi2 of x is not equal to 0 for all x belongs to I. So when we see this statement, we can clearly understand. Here comes the necessary and sufficient condition for any two solutions of a second order differential equation to be linearly independent. At the same time, we can also say this one as our characteristic equation of the two solutions phi1 and phi2 to be linearly independent. So the statement says any two solutions phi1 comma phi2 of a second order differential equation L of y equal to y double dash plus a1y dash plus a2y equal to 0 are linearly independent on an interval I, if and only if the Wronskian of x is not equal to 0 for all x belongs to I. In order to prove this theorem, Let us consider first of all the Wronskian of x is not equal to 0 for all x belongs to I. Then we will show that those two solutions are linearly independent. In order to prove the first part, let us consider C1 and C2 as any two constants such that C1 phi1 of x plus C2 phi2 of x equal to 0 for all x belongs to I. And finding its derivative, we are getting that C1 phi1 dash of x plus C2 phi2 dash of x equal to 0 for all x belongs to I. At the same time, the above two simultaneous equations in terms of C1 and C2 can also be represented in the matrix notation as written here in blue color. That is, the coefficients of C1 and C2 are collected in the first matrix, phi1, phi2 along the first row, phi1 dash and phi2 dash along the second row. So, we have considered the coefficient matrix in the first matrix and then the column vector that contains C1 and C2 that can be equated to the 0 matrix as mentioned here. According to our assumption, the determinant of the coefficient matrix is not equal to 0. So, in mathematics, we can say if any two terms are there in multiplication and their multiplication equal to 0 means we can conclude any one of them must be equal to 0, other one will not be equal to 0. As we have considered the determinant of the Wronskian is not equal to 0, the one and one possibility is that the column vector C1, C2 equal to 0. That means C1 equal to 0 and C2 equal to 0. That is the only one possible set of solutions for these two simultaneous equations. So first of all we have considered C1 phi1 of x plus C2 phi2 of x equal to 0. Now we got the conclusion that C1 equal to 0 and C2 equal to 0. Because of that reason we can conclude both phi1 and phi2 are linearly independent. Now, let us see the converse part. Conversely, let us assume that both phi1 and phi2 are linearly independent. Next, we need to show that both the Wronskian is not equal to 0. But as a contrary, let us suppose that the Wronskian is equal to 0 at some particular point x0 in I. So in the converse part, we are assuming that both phi1 and phi2 are linearly independent. Next, we have to show that the Wronskian of x is not equal to 0 for all x belongs to I. But as a contrary, let us assume that there is a point x0 in I such that the Wronskian at that particular point is equal to 0. So according to the definition of that Wronskian, we can expand the determinant and we can also write them in the form of the simultaneous equations as mentioned here. That is C1 phi1 of x0 plus C2 phi2 of x0 equal to 0. Similarly, from the second row we can write C1 phi1 dash of x0 plus C2 phi2 dash of x0 equal to 0. As these two are given in terms of C1 and C2, we can definitely call them as the simultaneous equations in terms of C1 and C2. So the values of C1 and C2 will be the solutions of these two simultaneous equations. As we have assumed the Wronskian of at the point x0 is equal to 0, definitely these two equations can also be represented in the form of matrices as mentioned there in the above first part. See, in the first part, how we are writing here these two simultaneous equations in the form of matrices. In the same way, it is possible to represent them these two equations also in the form of matrices. Anyways, as the Wronskian is equal to 0, the column vector C, that means the column vector that contains C1 and C2 cannot be equal to 0. That means these two simultaneous equations has a unique solution C1 and C2 where both of them is not equal to 0 simultaneously. That means any one of them must not be equal to 0. Any one of them must not be equal to 0 means definitely Such a solution can be taken in the linear combination in this format of C1 phi 1 plus C2 phi 2, and we are taking this linear combination by the new notation psi. Now definitely we are able to get L of psi equal to 0, because when we replace this psi by when we apply this psi in the above differential equation, that is in the place of y, here L of y equal to y double dash plus a1 y dash plus a2 y. This is what the given differential equation. And replacing y by psi, we can write here L of psi equal to L of C1 phi 1 plus C2 phi 2. Then that L operator, which is a linear operator, can be applied to each and every term separately here. So we can write then L of psi is equal to C1 into L of phi 1 plus C2 into L of phi 2. Already in the statement we are given that both phi 1 and phi 2 as the solutions of L of y equal to 0. So definitely they will satisfy the given differential equation, according to which we can say L of phi 1 equal to 0 and L of phi 2 equal to 0. So on the right hand side both the terms are getting 0. Because of that reason we are getting L of psi is equal to 0. Also, this psi will satisfy the initial conditions, because when we see the equations 4.4, the first equation can also be written in the format of psi of x not equal to 0 because of the expression of psi. Here, psi of x is given in the format of C1 phi 1 of x plus C2 phi 2 of x. Because of that reason, the first equation here can be written in the format of psi of x not equal to 0. Similarly, from the second equation, we are able to write psi dash of x not equal to 0. So, we are getting a new solution psi for the given differential equation L of y equal to 0. But already we are having that phi as our solution, where phi will be in the linear combination of both phi 1 and phi 2, which also can have the format C1 phi 1 of x plus C2 phi 2 of x. Because of that reason, we can apply the uniqueness theorem. By applying the uniqueness theorem, definitely we can say both phi and psi are equal. Otherwise, we can also say that psi of x is equal to 0. So, from which we are able to get C1 phi 1 of x plus C2 phi 2 of x equal to 0. Because of the uniqueness theorem, we are able to get psi of x equal to 0, psi of x is equal to phi of x is equal to 0, and then C1 phi 1 of x plus C2 phi 2 of x is equal to 0. So, according to our assumption of our converse part, we are able to get that both phi 1 and phi 2 are linearly independent, means C1 phi 1 of x plus C2 phi 2 of x equal to 0 must imply both the constants C1 and C2 equal to 0. But here we got the condition that not both the constants C1 and C2 are 0. At the same time, C1 phi 1 of x plus C2 phi 2 of x equal to 0. That gives a contradiction to the fact that phi 1 and phi 2 are linearly independent. Because of this contradiction, we can conclude the assumption what we have made in the converse part, that is the Wronskian at the point x not equal to 0 is a wrong statement. This contradiction shows that the assumption what we have made in the converse part is a wrong statement. Hence, we can conclude the Wronskian at the point x naught must be equal to 0 must be a false statement. Hence, the Wronskian at the point x naught must not be equal to 0. As it is true for all the points x in I, definitely we can conclude the Wronskian at the point x is not equal to 0. Hence, we can conclude that the given statement, two solutions phi 1 and phi 2 of L of y equal to 0 are linearly independent on an interval I if and only if the Wronskian of x is not equal to 0 for all x in I. In this connection, now let us see the outcome of this presentation. In this statement, we have just see the property of the solutions of an ordinary differential equation of order 2. From the above discussions, it is very clear that the Wronskian can help to determine whether the set of solutions to a differential equation is linearly independent or not. Even we can do many problems by using this property. In other words, it helps to establish whether the solutions form a fundamental set which is essential for solving linear homogeneous differential equations. So, checking for the solutions and for checking the linearly independent condition for the solutions, we can use the above theorem. And also, the above theorem is used for checking the existence of solutions. By examining the Wronskian, we can determine whether a particular differential equation has a fundamental set of solutions or not. If the Wronskian is non-zero at some point within the domain, it implies the existence of linearly independent solutions. Also, we are able to check the stability analysis. In the context of systems of linear differential equations, the Wronskian can provide information about the stability of equilibrium points. Specifically, it can help to determine whether the solutions approach or move away from equilibrium. So these are all the points we can understand, and for applying these concepts we can use the above theorem very well. Thank you.